Good, so welcome to this masterclass, and we're looking at Cambridge International Exams and AS level chemistry, and this is the paper 2 paper. That's the short answers, the structured answers from the summer series in 2014. Very good. Okay, so the paper starts off asking about ionization energy. And that's just the definition that you need to know. If I just write in here the equation that represents ionization energy. So it is that. And when the examiner was commenting on these questions, because there's 3 marks you can see there, most students were doing communicating this kind of idea, that you're forming an ion here because you're removing an electron. Students were fine on that, but they were weak on explaining that this was related to molar amounts and that it took place in the gas phase. You can see that I've written some state symbols in there. So you had to get the 3 marks, you had to talk about the fact that an ion was being created, the cation, that it's related to molar amounts and it's taking place in the gas phase. So to fully explain that, you'd say that the ionization energy is the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous ions. So that's the kind of language that you're using, but the key points that the examiner is looking for is the formation of the single cation, a molar amount, and taking place in the gas phase. So after you've done that definition, you then start to work with ionization energies, and there's a series of ionization energies here. It says the first 7. Technically that's known as successive ionization energies, and you've got to figure out which group from the periodic table this is most likely to belong to. So you've got to spot that's the first ionization energy in these series of successive ionization energies. That's the first, the second, the third, the fourth, the fifth, the sixth, and the 7th ionization energies. And you need to be spotting that in between the 5th and the 6th, there's a big jump in the ionization energy. Of course, they're all positive. Of course, they're all increasing. We're taking electrons away from an increasingly positively charged cation. They're going to get increasing values, but there's this big discontinuity here, this really big jump. And so the examiner is expecting you to say that that means that those 5 ionization energies refer to electrons being removed from the outer shell. And then once those have all been removed, you're starting to remove electrons from an inner shell. And that's because you see this big energy difference here. And you're removing electrons from the inner shell here. They're inner electrons. They're much, much more closer to the nucleus. There's a stronger electrostatic force of attraction between the electrons and the positively charged nucleus. And they're much closer, and you're going to need much more energy to overcome that electrostatic force of attraction because these inner electrons are closer to the positively charged nucleus. So you could say, well, this is group 5, and that would get you the mark, but the data book and actually the UPAC official periodic table now lists group 5 as group 15. So really, to be absolutely perfectly correct, you're removing electrons from an atom in group 15. Historically, that's group 5, or maybe for a Roman symbol, V. But group 15 is really what you should be doing. And for your marks there, you're saying there's a large difference between the 5th and the 6th ionization energies, because the 6th electron is being removed from an inner shell. Or perhaps you could describe that as a noble gas core. And because you're removing the electron from an inner shell, then these core electrons are much closer to the nucleus. They're much more strongly attracted to the nucleus, and you need this higher energy to remove them. So that's where you're getting your 2 marks there. Okay, so you've got to complete the electron configuration for this element in group 5. Well, you're going to have, aren't you, 5 electrons in the outermost shell, and it's in period 2. So you're into the second shell. And well, how are you going to fit 5 electrons into the second shell? Well, you'll fit 2 into the s atomic orbital, and you'll fit the remaining 3 into the p atomic orbitals. So if you wanted to write that out by hand, you'd have 1 s2, then you've got the 2 s2, and then you've got the 3 electrons in the singly occupied p orbitals there. You've got 1 s2, 2 s2, and 2 p3. Okay. Now, what the examiner noticed was that some students went actually for period 3 for some reason, and I think that's because when you look at the periodic table, only hydrogen and helium are in period 1, and then you drop down to period 2. So this actually there is period 1, just hydrogen and helium, and now we've moved into period 2. And because hydrogen and helium are in such a small period, there's only 2 elements in it, a lot of people don't recognize that as period 1. So you just need to get these horizontal rows of the periodic table clear in your mind. Period 1 just has hydrogen and helium, and then you're into period 2, and this is now group 5, better said, as group 15 in period 2. Okay, so next one, the relative atomic mass. Well, I could just say you should go and look that up. You can do, but the examiner was picking up that a lot of students answered this really, really badly, and only the top students, the A-star students, were getting this really tightly defined. So if you want to push your grade up, then this is one of the definitions that you've got to be really sharp on. And what the examiner was looking for was that the relative atomic mass is the weighted mean of the mass of an atom of an element relative to 1/12 of the mass of an atom of carbon-12. So let's just, I'm not going to write that out, you can look that up in your textbooks, but what the examiner was looking for in these marks here was first of all something to do with a weighted average or a weighted mean. And what that means is that for each element there might be a number of different isotopes. For example, for chlorine, you know, there's a chlorine-37 and a chlorine-35 isotopes, and the weighted mean is the use of the percentage abundance for each of those different isotopes. So, for example, in the case of chlorine-37 and chlorine-35, there's about 25% is chlorine-37 and about 75% is chlorine-35. And so the weighted average is closer to 35 than it is to 37. So the weighted average relative atomic mass for chlorine is 35.5. So we need this discussion, or this this note here, that it's a weighted mean of the relative isotopic masses. So we needed that there in the definition. And because it's relative, well, what is it compared to? This is a comparison, something being made relative to something else. So you've got to compare the mass of an atom to something else. And what you're comparing it to is 1/12 of the mass of an atom of a particular isotope of carbon, carbon-12. So you can see here, you need to write out the full definition, but the main points the examiner is looking for is this, sense of a weighted mean or a weighted average, and that you're comparing it, it's a relative atomic mass, and you're comparing it to carbon-12. Specifically, you're comparing it to 1/12 of the mass of an atom of carbon-12. Good, so now you've been through the definition, you've got to do a bit of a calculation here. And the best way to think about this is that you've got this unknown element, and you've got, you know, that it's in a compound with chlorine. And it's told you in the question that the percentage by mass is 31.3 for this unknown atom. So 31.13, isn't it? And for chlorine, it's 68.87. Okay, we had those values up here, didn't we? There they are. Good. All right, now I'm just going to go through this in quite a lot of detail just to make sure we don't leave anything unturned, any stone unturned. But when you've got this percentage, that means in 100 grams, your mass of Z, which we don't know, and chlorine, you know, this is a bit pedantic, but that would be a mass of 31.13 grams and 68.87 grams. We're just saying, well, in 100 grams, if those are your percentages, these are the masses of Z and the mass of chlorine. Now, you can look up in the periodic table these relative atomic masses. Now, we don't know, we're just saying, that's what we're trying to find. We're trying to find out X. We don't know what the relative atomic mass of Z is. We'll just call that X for the moment. But we can look up chlorine. And we said earlier that's 35.5. Now, to be strictly careful here, we should know that these relative atomic masses are the same numerically as the molar mass, but the molar masses are expressed in grams per mole. So we don't know what that is. And the molar mass for chlorine is 35.5 grams for a mole of chlorine. So we've got a mass over here, and we've got a molar mass over here. And you should know the relationship of the amount, the number of moles, is the mass of, divided by a molar mass. And that gives us the number of moles, the amount. So the next column along here is the amount, the number of moles. And to get the number of moles, you're going to divide the mass that we had there by the molar mass. So for chlorine, we've got to divide 68.87 grams by 35.5 grams per mole, and that gives us an amount of 1.94 moles. All right. Now, we know from the question stem up here that the relationship between the number of moles of chlorine and the number of moles of Z is 1 to 2. So if we've got 1.94 moles of chlorine, then the number of moles, the amount of Z, must be half of that. So that's easy, just divide 1.94 moles by 2, and we end up with 0.97 moles of Z. Now, at this point, we've got, for this unknown atom, or this unknown element here, we now know the mass, don't we? And we now know the amount. So that must mean we can calculate the molar mass. You just have to rearrange this. You can see now that the molar mass, that's capital M, is equal to the mass, isn't it? Whoops, divided by the amount, the number of moles. So we've got to take our mass here and divide it by the number of moles. And if you divide 31.13 by 0.97, then you end up, let's do that, 31.13 divided by 0.97, 31.13 grams divided by 0.97 moles, then you get an answer of 32, pen's not working for me, let's rub that out. You get a result of 32.0927. I'm just writing out, I'm not rounding too early here. And the units there, of course, is grams divided by moles, grams per mole. That's the molar mass. But the relative atomic mass of an element is the same as its molar mass, but without the unit. The numerical value is the same. And so the relative atomic mass for this element is 32.0927. But the question is saying, isn't it, that we've got to go for 3 significant figures. All right. So if you look at this, well, 3 significant figures is going to give us a result here of 32.1. And because this is a relative atomic mass, it's compared to something else. It's relative. There's no units. So our answer there, 32.1. Now, talking about chlorides in period 3 here, aren't we? There we go. Now, and it's going to be adding these 2 different chlorides to water, and wants you to tell you, you've got to write equations to show what happens. Well, you know, of course, sodium chloride is just salt. So when you add salt to water, what are you doing? You're just dissolving salt. So very, very simply, you've got sodium chloride, that's solid, and you've got an excess of water. I'm just going to put a Q to represent an excess of water, and I'm going to get the sodium ions, and they're hydrated, so I put AQ there as the state symbol, and Cl- ions, again, they're hydrated, so I put the state symbol there. All that's happening in this first step is that an ionic compound is dissolving in water. That's it. Now, next one, you've got silicon tetrachloride, and this is just a reaction that you need to know. You dissolve that in water, and then it reacts with the water, and you get steamy fumes. Now, those fumes are hydrogen chloride gas, and so if you balance this all up, you end up with silicon dioxide there, and the hydrogen chloride gas, which is being produced. And you've got to have a stoichiometry there, haven't you? That all balances up. So that's a liquid, that's a liquid, that's a solid, and that's a gas. Good. Now, coming down here, you've got quite a lot of marks to score here. You've got 4 marks, and you've got quite a dense question stem because it's asking you to state and then explain the differences between the 2 chlorides in terms of their structure and bonding. So you've got things to state, things to explain, you've got to use ideas of structure and of bonding. And so really you've got to do this comparison of these 2 chlorides. You've got sodium chloride and silicon tetrachloride. Well, you need to state the difference in behavior. Well, the sodium chloride, that just dissolved. And that's different to the silicon tetrachloride because that reacted. So we've stated, and we've got to talk about the bonding. Well, you know, sodium chloride is ionic. The bonding in silicon tetrachloride is covalent. And it talked about the structure, didn't it? The structure of the compounds. This is a giant lattice, a giant repeating pattern of ions. And this is just a simple molecular compound. It's composed of discrete small molecules, a simple molecular compound. And those molecules internally have atoms that are bonded covalently. And so we've stated the differences in behavior. One was dissolved, one reacted. We've talked about the bonding and the structure, and we've got to explain, that was the last thing, wasn't it, for our 4 points. And you could just say here that the ions in sodium chloride are hydrated. And here you're going to say that the compound reacts. There's not really much more you can say. You can say it reacts to form new substance. Yeah, that would be a pretty full description of what's going on in a chemical reaction. But you can see we had to sort of deconstruct the question stem quite carefully to make sure we got our 4 marks: stating and explain, looking at structure, and looking at bonding. Okay, so again, question stem we're looking for the shape and a bond angle in this simple molecular substance as well. But this time they've sort of laid it out for us, so it's quite clear that we've got to state a shape and a bond angle. Okay, so the shape, you've got SF6, and when you get 6 atoms around a central atom, then the shape that you're going to get is octahedral. The bond angle in octahedral is 90 degrees. Well, why is that? Let me just draw it out. They haven't asked for it here, but it's important. You've got a central atom, and then around the central atom, you've got these two fluorine atoms. They're called axial. And then, well, if you had to draw it, sometimes when they ask you to draw these, you've got to make sure that you're drawing these wedges coming out of the plane of the paper and going behind the plane of the paper. So these are your fluorine atoms. Okay, so, but you can see that you've got a square of these axial fluorines, and then what am I talking about? Not the axial, the equatorial. Okay, so these 4 are equatorial, the one above and one below are axial, and those 4 are in a plane, and the bond angle between them there is 90 degrees. And because there's one fluorine atom above and below the plane, then the angle with the plane is also 90 degrees. So each sulfur fluorine bond angle is generally 90 degrees. They haven't asked you to draw the 3-dimensional structure. If you had to do that, you'd have to have those wedges coming out of the plane of the paper and going behind the plane of the paper as well. Good. All right. So there's a fairly sort of dense question stem up here, but that's not too bad because, as you probably spot, they're going to lead you through working with all the information in that question stem. Now, in this question, this oxidizing agent, manganate 7, is being added to a solution that contains Fe2 plus ions. And it says, well, as you do that, the manganate 7 is going to oxidize these Fe2 plus ions. And so you've got to explain what this term oxidize means. You could use your mnemonic, Ulrich, oxidation is loss. Well, you could say, well, oxidation is loss of electrons. But because it's asking for the meaning of the term in the sentence, it's not sufficient just to say oxidation is loss, because you haven't given the context of oxidation in this sentence above. So you've got to say that the ion 2 plus ion loses an electron. Okay? Because oxidation is loss of electrons. And what the examiner said when you check back through the examiner's notes is that it's not sufficient just to use your definition of oxidation. Oxidation is loss of electrons. You've also got to contextualize what you're saying, because it's asking about the meaning of this term in the sentence above. So you've got to say, well, oxidation is loss of electrons, but in this particular case, it's about an ion 2 plus ion losing an electron. Now you can see that here, can't you? That 2 plus ion has lost an electron and formed Fe3 plus ion. And you've got to balance that equation up. What I would do here is start balancing on the right-hand side. We had 4 oxygens over here. I'm going to have 4 oxygens over here. That's balanced. Now I've got 8 hydrogens here. I've got 8 hydrogens there. And that all balances up. And you've got Mn2 plus there. So I think that's the only fact that you had to know, was that when you do these titrations with this deeply purple manganate 7, then you end up with, don't you, a solution of these manganese ions that is essentially colorless. Actually, it's very, 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 very pale pink, but it's so pale that it's difficult to see the pink. So they're basically colorless when you do these kinds of titrations. But you're going from manganate 7 over here. This is the manganese 2 ion in solution. Now you've got the stoichiometry of that all worked out. You've got to calculate the number of moles, the amount of manganate 7. Well, you're just using, aren't you, your relationship that concentration is amount, number of moles, divided by volume. Now you need the number of moles, the amount, you just rearrange that equation. The number of moles, the amount, is equal to concentration times the volume. So we know the concentration up here. What was that? The concentration was given to us as 0.02 moles per decimeter cubed, and the volume was 20 centimeters cubed. But just watch it. The concentration is moles per decimeter cubed, and so you've got a volume here that's in centimeters cubed. You've got to change that from centimeters cubed to decimeters cubed. You do that by dividing by 1,000. And so you do that calculation, and you end up with 4.00 times 10 to the minus 4, and we're working with an amount, the number of moles, so the unit there is moles, MOL. And you can see here that I'm getting my answer to 3 significant figures, because in the question I've got 3 significant figures there, 3 significant figures there, 3 significant figures there. So I'm being consistent by having the smallest number of significant figures that is given in the data in the question as the number of significant figures that I'm using to give my answer here. So that's 4.00 times 10 to the minus 4 moles. Now, it's really talking you through things here. You've got to use the answer that you got there and the stoichiometry that you worked out here to calculate the amount, the number of moles of iron 2+. Well, you've got a stoichiometric ratio of 1, haven't you, to 5. And if you know that that is 4 times 10 to the minus 4 moles, then this must be 5 times that. So you've just got to do a little bit of a calculation. 5 times 4 times 10 to the minus 4. That was the number that we had up there. And that's going to give us 2. I'm going to keep going with 3 significant figures so I don't lose precision, times 10 to the minus 3. And we're talking about an amount, aren't we? So that's units of moles. And that's the number of moles in 25 centimeters cubed, because we were doing the titration earlier on. Now, if you remember, this 3.4 grams was not dissolved up in 25 centimeters cubed. It was dissolved up, if you look back at the question, in 250 centimeters cubed, isn't it, up here? It was dissolved up in 250 centimeters cubed. And then we took a 25 centimeter cubed aliquot of that later on. So to work out actually the amount in the original solution of 250 centimeters cubed, you're going to have to take the amount that you had in 25 centimeters cubed and work out how much was in 250 centimeters cubed. Well, you know, that's the original volume was 10 times the volume that we used in the titration. So the number of moles of this compound in 340 grams was 2.00 times 10 to the minus 2 moles. Good, so they're really stepping us through this calculation here, aren't they? So you've now got to calculate the relative formula mass for that. Okay, now relative formula mass is the equivalent of relative molecular mass for things that aren't molecules. This is the repeating unit in a giant lattice in an ionic compound. But the relative formula mass is unitless. Again, it's a comparison. It's a comparison actually back to 1/12 of the mass of the carbon-12 atom again that we had earlier on. But you need to know that to get a relative formula mass, you can just work out the molar mass, that's units grams per mole, and then these relative masses are the same as the molar masses, but without units, because they're relative, and these are described in units of grams per mole. So we know, don't we, that there's 2 times 10 to the minus 2 moles. Well, let me just clear up that pen. I'm trying to write moles here. There's 2 times 10 to the minus 2 moles in 3.4 grams. So we've got, haven't we, an amount, and we've got a mass, and we just have to use this equation again, that the amount is related to the mass and the molar mass in this equality, that the amount is equal to the mass divided by the molar mass. On this occasion, we want to find, don't we, the molar mass. And so we just rearrange that, and the molar mass is equal to the mass divided by the amount. Here's our mass, here's our amount. To get the molar mass, we're going to divide the mass by the amount. So you've got 3.40 divided by 2 times 10 to the minus 2. 3.40 divided by 2 times 10 to the minus 2 moles, and that's in grams, isn't it? And that's going to give us an answer of 170 grams per mole. You can see grams per mole in that calculation there. Excuse my writing, grams per mole. But we want not the molar mass, but the relative formula mass, and that's numerically the same without the units. And so the answer to that is that the relative formula mass is 170. Now, we've got that. We've just got to calculate the value of X. Well, we know that the mass of 1 mole of this compound, we've just calculated, haven't we, is 170 grams. That, you know, that the molar mass was the number of grams per mole. So the mass of 1 mole of this is 170 grams. They've told us here that the mass of 1 mole of the anhydrous salt, no water, is 151.8. So the difference between those must be the mass of water in 1 mole of FeSO4 XH2O. Do that subtraction and you end up with 18.2 grams. So in 1 mole of this, there is 18.2 grams of water. And again, to go from, that's a mass, isn't it? To go from mass to amount, you're using amount equals mass divided by molar mass. We've got the mass there. And the molar mass of water, you can just look that up using a periodic table. The molar mass of water is 18 grams per mole. And so to get the amount of water, you've got to divide 18.2 by 18. You've got to divide 18.2 grams by 18 grams per mole. And that gives you the amount of water, the number of moles of water in 1 mole of the substance is, you do that calculation, it comes out as 1.01 moles. Now, at this point, of course, you recognize that you're going to have whole number ratios. You can't have X as 1.01. And so the nearest whole number ratio that you can get is 1. And so the value of X in FeSO4 XH2O is 1. It's FeSO4 H2O. The value of X equals 1. So just some early warning here. This question was picked up by the examiner as not being particularly well done. Some early warning for you. They're flagging up here that you've got to make sure that you know when you're talking about atoms and when you're talking about ions. ions, okay? A halogen atom or a halide ion. So be careful with your language. Now, we've got these substances here. We don't know what they are. They're either halogen atoms or halide ions. We know that. And we're adding sulfuric acid to NaK. And that's going to produce white fumes that turn blue litmus paper red. Well, if the blue litmus paper is being turned red, then that means an acid is present. And it says here, we've got fumes. Okay, so there's an acid gas. Yeah. Well, what gases do you know that are acid that might be connected with halide ions? Well, you know, that sounds like, doesn't it, hydrogen chloride gas. So what's our equation here? We've got, and excuse me, let me try and get my writing done a bit better for you. We think we've got hydrogen chloride gas, and so we've got sodium chloride. We wanted to have a concentrated sulfuric acid, H2SO4, and we're going to be making hydrogen chloride gas and the sodium salt of sulfuric acid, which is sodium sulfate there. And just to balance that up, you've got to have 2 sodium ions there, haven't you? That all balances. And that as well. Okay, so the identity of K, well, you've got to be very careful here because you don't want to say a halogen atom, you've got to say the chloride ion. So don't say chlorine, you need to say chloride ion. Yeah? Good, all right. So those are your 3 marks there. Now, next one, we've got this halide. When we add it to silver nitrate, we're getting a precipitate, and that precipitate remains even after we've added concentrated ammonia solution. So, I mean, you can probably guess what's going on here. They're testing, aren't they, your knowledge of bench tests for halide ions. So what's going on here is you're expected to know how you discriminate in the laboratory between chloride ions, bromide ions, and iodide ions. Well, first of all, you add, silver nitrate solution, and the chloride ions form a white precipitate. Bromide ions form a cream precipitate, and iodide ions form a yellow precipitate. Now that should be enough, shouldn't it, to discriminate between chloride, bromide, and iodide ions, but you know, it might not be that easy to be absolutely sure between white and cream, or between cream and yellow. So to be completely sure, then you can add ammonia solution, and this white precipitate of silver chloride will dissolve in dilute ammonia. This precipitate will dissolve, excuse my writing, I'm still learning to use this pen, will dissolve in concentrated ammonia, and this silver iodide precipitate, this yellow precipitate, is insoluble in both dilute and concentrated ammonia. So that's how you distinguish between the chloride, the bromide, and the iodide. And so if you come back up here, you've got to use that knowledge to work out what this halide ion here, when it forms a precipitate that doesn't dissolve in concentrated ammonia. So that must mean that the identity of L is this iodide ion. Okay, make sure you're not putting iodine. It's an iodide ion. The color of the precipitate is yellow, and it's a precipitation reaction. You have to write the ionic equation. So you've got you just miss out the spectator ions. So you've got the silver ion in solution, and you've got the iodide ion in solution, and when those mix together, then you get this precipitate of silver iodide as the precipitate is forming, and it's not soluble even in concentrated ammonia solution. Last one, you know that the halogen elements form these diatomic molecules. So M2 is a liquid at room temperature. It's got a higher boiling point than chlorine, but a lower boiling point than iodine. The identity of M is bromine. Now, strangely enough, the mark scheme said Br2, and that's wrong, actually, isn't it? Because Br2 is the molecule, but the identity of the atom within that molecule is bromine. Okay, nothing to do with bromide ions. Actually, if you said Br2, that's not completely correct. And this is not bromide, but bromine. So we're distinguishing between an atom and an ion, and that got flagged up in the question stem, didn't it? And you've got to explain, haven't you, why the boiling point of these bromine molecules, Br2, is greater than Cl2, but less than I2. And so you've got to use ideas of intermolecular forces between molecules. Now, these molecules here, well, obviously there's no hydrogen bonding, there's no hydrogen present, but the molecule is non-polar, isn't it? It's got a bromine joined to bromine. There's no positive or negative end to that molecule. It's non-polar. But even for these non-polar molecules, the kind of forces that you can have between non-polar molecules are called London forces, or you sometimes see those as dispersion forces. These are the weak intermolecular forces that exist between all molecules, actually, but the only possible forces that can exist between these non-polar molecules are these London forces or dispersion forces. By the way, London is nothing to do with the city of London, the capital of the United Kingdom. It's named after German professor Fritz Wolfgang London. So that's the forces are named after a professor, not after a particular city, just in case you're wondering about that. Okay, so these, and just as way of explanation, although these forces have names, either London forces or dispersion forces, if you want to describe them, you could say that they are temporary and they're instantaneous dipoles. So these are temporary, instantaneous dipoles. And what happens is if this is a bromine molecule, it's got two bromine atoms joined together, on average, all the electrons are spherically around that bromine atom and spherically around that bromine atom. But at any one particular time, in any particular instant, the electron cloud, if you think of these electrons around these bromine nuclei as a cloud of electrons, at any one particular time, there might be more electrons over here and less electrons over here. And so you would have a temporary, at one particular instant, a temporary instantaneous dipole. So that might have a slightly positive end and a slightly negative end at one particular instant. If you averaged it over time, all these dipoles will cancel out. And so it's just a temporary dipole that exists for an instant. It's just like a fleeting event that happens. And because you've got suddenly a negative end to that dipole, then the neighboring molecule will have an induced dipole. So these electron clouds will get the force of repulsion. These electron clouds will move, so you get a temporary induced dipole there. And just for that fleeting instant, when there was a temporary dipole here, and the induced dipole in the neighboring molecule, then you'll get just for a moment these dispersion forces, or this London force, this intermolecular force. And that's sufficient to have overall a small or a weak intermolecular force between different molecules. Now you can see that if these electron clouds are large, then they're going to be much more easily polarized than if they are tightly bound to a nucleus. So if you've got a large atom or molecule, and if you've got lots of electrons, then this polarization that's happening here, this induced dipole, is going to be happening much more easily than if we had a small molecule with tightly bound electrons and a small number of electrons. So you've got to get all that kind of language into this explanation here. And really, you're going to be talking about bromine molecules having more electrons than chlorine, but less electrons than iodine. And you're going to be talking about bromine molecules being larger than, excuse my writing, than chlorine, but smaller than iodine molecules. So that's where you're getting your 2 marks there for these weak, weak intermolecular forces, which are technically either called London forces, they're both exactly the same, or dispersion forces. So I think to get all your marks, you've got to have weak intermolecular forces that are London forces or dispersion forces, and you need to say that bromine has more electrons but less electrons than iodine, and bromine is larger than chlorine but smaller than iodine. So you're working quite hard there, I think, to get your 2 marks. Generally, the examiner found that students answered this question very, very well. It's actually GCSE knowledge, so it's not strictly A-level knowledge. This is the industrial electrolysis of sodium chloride solution, concentrated brine. And what you get coming out here is chlorine gas. What you get coming out here is hydrogen gas. And what comes out here is a solution of concentrated sodium hydroxide. So you just had to put, I've done it, haven't I? Chlorine, hydrogen, and sodium hydroxide as the products of the electrolysis of sodium chloride solution, brine. Now you've got to give equations for the 2 electrode reactions, okay? Now that means you've got to know what happens at the anode and what happens at the cathode. So there's lots of different ways you can remember this. Let me just go through them. You can pick which ones you want. Anions go to the anode in electrolysis, and cations go to the cathode in electrolysis. So that's one way of thinking about things. If you can't remember your anions and cations, well, there's some things to help you. You could say that a cation, the letter T in there, you see that, is like a positive charge. So that the cation is positive because the word cation has a T in it, which looks like a positive charge. So cations are positive. You could say, this is really bad, by the way, that a cation is, and English speakers will get this. Okay, I've spelled positive wrongly, but a cat has pores, so a cation is positive. Sorry about my bad joke, but that's one way to remember this. Or if you're not happy with the T being like a positive, or the cat having pores, a cation being positive, then slightly more rigorous is an anion is a negative ion. So a negative ion, a negative ion, an ion, anion. So that's some different ways of remembering this. Other ways, I'm just giving you loads of stuff here. Sometimes you see that this word CROA, it's just kind of a made-up acronym. At the cathode, there's a reduction. At the anode, there's an oxidation. You might need to check that a bit later on. But you can you can use all those kind of tips and tricks and tools to remember that what's happening at the anode, well, the anions are going to the anode. The anions are negative, so the anode must be positive. Let's just check that. Yep, the anode is positive, and chlorine gas is being made there. So the anion, which was a negative ion, went to the positive electrode and made chlorine gas, didn't it? And we're just multiplying it by 2, so we've got the stoichiometry correct. And at the anode is oxidation. And oxidation, another mnemonic, oxidation is loss, that's our oil rig mnemonic. Oxidation is loss, so we're losing electrons. There they are, they're on that side of the equation. State symbols, that's in solution, and the chlorine gas is released, the electrons go onto the anode. So we got that all right. The cations go to the cathode. These are positive ions. Well, actually we've got, the water is ionizes slightly, doesn't it? So you've got that equilibrium, you've got hydrogen ions, and you've got hydroxide ions. And so what's going to the cathode? Well, the positive ion is going to the cathode. So that means you've got H+, and when it gets there, it's going to be making hydrogen gas. We've got to multiply it by 2 to get our stoichiometry correct. And we know that at the cathode, where the cation went, which was positive, then at this mnemonic here, CROA, at the cathode you've got reduction, and reduction is gain of electrons. Well, if we're gaining electrons, then they go on this side of the equation. There's 2 of those, and 2 hydrogen ions gain 1 electron each, 2 electrons altogether, to give us a hydrogen molecule. That's a gas, and the hydrogen ions were in solution. So, you know, if you don't know anodes and cathodes and anions and cations, if you can't remember that, there's a whole bunch of sort of mnemonics and memory aids that help you get that. Good. All right, next question. Talking about the differences between alkanes and alkenes. Okay, so 2 marks here. And the question stem is asking how and why bromine is used to distinguish between an alkene and an alkane. All right. So for an alkene, excuse my writing again, bromine is decolorized, excuse my writing, in an addition reaction. The bromine adds to the alkene, and as that addition reaction happens, the bromine is decolorized because the resulting product, the dibromo compound, is itself colorless. And that's a really easy test. It happens at room temperature. It's really easy to do. It's just a kind of lab test for trying to pick up whether you've got an alkene or not. For an alkane, well, it does react with bromine, but only with ultraviolet light to initiate the radical substitution reaction. So the first one is an addition reaction. The second one only happens with ultraviolet light, and that's a radical substitution reaction. Now, it's now talking about this radical substitution reaction of ethane with bromine. Okay. Now, the essential conditions for that is you need ultraviolet light to initiate the reaction, and that's where you're going to get your 1 mark. Now, the full name of the mechanism for that reaction is, well, it involves radicals. And as you step through the mechanism of that reaction, then hydrogen atoms in ethane are being replaced or substituted with halogen atoms. So it's a radical substitution. Now, the examiner, when the examiner provided comments on this, the examiner was saying that this radical substitution reaction was really, really badly known by lots and lots of students. So the A-star students are the ones that are getting the mechanism for this radical substitution reaction correct. So if you want to be an A-star student, this is one area where you've got to focus. You've got to learn, you've got to understand this radical substitution reaction. So we're just going to spend a little bit of time just going through that, because this is one of the places where the marking clearly discriminates between the A-star student and the other students. So I just need a bit of space to be able to do this, which is quite tricky. Have I got a page in it? Well, I've got some space over here, so I'm going to use this, okay? Just to go through all of this. So you need to know that in these radical substitution reactions, there are three parts to the reaction. I mean that's the thing that you probably know. There's the thing that starts, or the step that starts off the process, the initiation. Then there's the step that continues, or allows the reaction to continue. That's the propagation reaction. And then there's the step that allows the reaction to finish. That's the termination reaction. And in this initiation reaction, you are going to produce radicals. And in the termination step, you're going to consume or use up radicals. And what's tricky or interesting about this middle step, the propagation step, is that radicals are consumed and, in the propagation step, radicals are produced. And that's why this propagation step keeps the reaction going, because even though it consumes radicals, it also produces them. And so it keeps the reaction going. And that's generally, the examiner is saying, the difficult step for students to get. So let's take the simplest example of an alkane reacting with this bromine atom. Simplest alkane, I'm going to write this out, be really explicit about it. We'll just take the simplest possible one, is methane, and that's going to be reacting with the bromine molecule. Now, what's happening here is in the initiation, is ultraviolet light is used to break this bromine-bromine bond. And it breaks it in such a way that the two electrons that are in that bond, remember a covalent bond is made up of two electrons, it's going to break it so that one of the electrons that's in that bond goes to that bromine atom on the left, and one of the electrons that's in that bond at the moment goes to the bromine atom on the right. And that bond breaking, where one electron goes to the left and one goes to the right, is called homolytic fission. And in chemistry, that's represented with an arrow, but just half an arrowhead, because there's only one electron. So one electron goes there, and the other electron in the bond goes there. And that gives us the bromine atom that was on the left with one electron, and the bromine atom on the right with one of the electrons that was in the bond as well. And these two bromine atoms have got an unpaired electron, and so those are radicals. And you can see in this initiation step, the initiation step is characterized by producing radicals. And here we've produced these two bromine radicals because the bond was broken homolytically. One electron went to the left, one electron went to the right. Good. Now, in the next step, here's our methane molecule again. I kind of draw it a bit early just to introduce it. So that's not involved in the initiation step. It's involved here, I don't know why that happened, in the propagation step. So here's the methane molecule, and here's one of those radicals that we made in the initiation step. And again, we're going to get homolytic bond fission. And what's going to happen is that one of the electrons in this bond is going to go there, and one of the electrons in that bond is going to go here, and that electron is going to go there. So you can see now one electron has come here, one electron's gone there, two electrons, that's going to make a covalent bond, and the other electron that was in that bond there has come on to the carbon atom. So that gives us we've made that bond, haven't we? We've made it from there and there. So that's that bond formed. And one electron went there. The other electron came onto the carbon atom. We've now got a radical from the methane molecule. And so the propagation step is consuming a radical and producing a radical. Now you can see that we've consumed one radical there, we've produced another one, and that continues to go on in this next propagation step, where you've got another molecule of bromine, and that's going to start to form a bond there, and that's going to have homolytic fission. That's going to, one of the electrons from that bond is going to go on here, and the other electron is going to go there. And so we end up with a new covalent bond formed here from two electrons. And we end up with this radical formed over here. Now, if you look, during this propagation step, we consumed a bromine radical and we produced a bromine radical. So as far as the reaction is concerned, a bromine radical is still available at this end of these two propagation steps and can go on to trigger more propagation steps as well. So that's the tricky part, this propagation reaction, because there's two steps within the propagation step itself. And then finally, the termination step that consumes radicals. Well, there's lots of different ways that could happen. You might have two bromine radicals reacting together. If I drew in the mechanism for those, you'd have that, and you'd have that, and they're going to bromine molecule. Or you could have two of these, I'm running out of space here, two of these fragments that were derived from the methane molecule, those two fragments, they could go on to form a new covalent bond between the two carbon atoms, like that. And you've ended up with a termination because there's no free radicals left, the free radicals have been consumed, and you've ended up with a two carbon molecule here. You've ended up with ethane. There's lots of different possibilities in which the reaction could end, reaction could terminate. So we've done quite a lot of detail there, but I just wanted to do that because the examiner's saying, you know, the thing that discriminates or distinguishes between the A-star student and the other students is a knowledge or a really good understanding of all the mechanisms in this free radical substitution, initiation, propagation, and termination. Okay, so you could give a termination step that could occur producing a hydrocarbon. Well, we've got ethane that's reacting here, haven't we? So a possible termination step, well, just going back to the comparison that we had with the methane molecule that I gave you just now, if this was ethane molecules, then you'd have those two radicals, wouldn't you? And you'd end up with a 4-carbon chain, C4H10, those two radicals being consumed to form a hydrocarbon. Now, in this next point, it's asking for one of the propagation steps. Now you can see up here in the propagation step, there's actually, there's two steps, aren't there? There's two steps up here. Yeah? And it's just asking for one of those. All right? So for one of those, let's take the first one up here. You could do the second one, but we'll just take the first one because the question is asking for the first one. So it's saying, well, we're going to start off with I'm going to just put the bromine down here. And then you've got your bromine radical. Well, what's going to happen? It's going to be exactly analogous to the long description that we did with methane up there. You're going to get homolytic fission of the carbon-hydrogen bond there. You're going to get one electron coming here, and you're going to get that electron coming there. That's going to form a new covalent bond between the hydrogen and the bromine. We're going to get hydrogen and bromide forming there. And then the other electron that's in that bond pair, you see one of them went here, the other one is going to go there. So you're going to end up with that, aren't you? Okay, so you've got C2H4Br, but a radical molecule, yes? So the propagation step that you're going to have in here is the one we just wrote out with the displayed formulae just now. We started with that molecule, and we had the bromine radical, and that's reacting, isn't it, to give you, sorry, my arrow not drawn very well, C2H4Br, and remember that's now the radical, and we've got this new covalent bond that's formed hydrogen bromide. So if we're just looking for one of the steps in the formation of dibromomethane, that's the first step. If we went through the second step, then we'd be doing the analogous part to this step here, but we just did the first step there. And that's something that you've really got to work hard on, because if you're going to be an A-star candidate, understanding these propagation mechanisms is what distinguishes you as an A-star student from the other students. Okay, going back now to ethene. Okay, well, what's happening in this reaction is that you're getting an addition reaction, aren't you? We'll do the mechanism for it in a moment. And the name for that is an addition reaction. We talked about that earlier on. We're adding bromine across the double bond, and we'll see why in a moment. It's an electrophilic addition. Yeah, and that's become a bit clearer once we do the mechanism, which is the next step down here. And what's going to happen is that this area between the two carbon atoms is really electron rich. You can see there's a double bond here. So that's a very electron rich atom. The bromine molecule can be polarized. The electron cloud around it can be distorted. And as the bromine molecule approaches this area of strong or high electron density here, then the bromine molecule is polarized, and its electron cloud is pushed away, it's repelled, so it ends up with a dipole at one end of the molecule, slightly negative, and a dipole at the other end of the molecule, slightly positive. Now, once this dipole has been induced, then you can move a pair of electrons. It's going to move there. Okay. Now you have to be quite careful when drawing these arrows. You've got to draw the arrow from where the pair of electrons started to where the new bond is being formed. Okay. So the electrons are moving from that double bond to form a new bond with the bromine atom. And as it does that, this is going to be that bond pair of electrons is going to move onto the bromine atom at the end of the molecule. And so as that happens, you're going to end up with an intermediate. So all these atoms are still in their place, but we've lost that double bond now, haven't we? That the bond pair of electrons formed a new bond to the bromine, and the bond pair of electrons moved off the bond there onto the bromine atom to give you a bromide ion, and that's the bond pair of electrons there. And because the bond pair of electrons moved, you've ended up with a carbocation. You've got a positive charge on the carbon there. Now, in this next step, to go from the intermediate to the final addition product, where you've got a bromine atom on each of the carbon atoms, then you've got to show that bond pair of electrons forming, haven't you, the bond to the carbon atom. So that's a bond pair of electrons on the bromide ion, and they're moving there, and they're attracted to this carbocation, this positive charge on the carbon here. And so the examiner has given you 4 marks for getting this mechanism right. And again, this is the kind of thing that marks you out as an A-star student. You've got to get 1 mark for that induced dipole in the bromine molecule, and you've got to get 1 mark for these curly arrows with the double-headed arrow here. And then as you move here, you've got to show the intermediate with the positive sign there, and you've got to show the curly arrow moving from the lone pair of electrons on the bromine atom, form a new bond between the bromine atom and the carbon atom. And so you're getting 1 mark for the intermediate and 1 mark for the correct curly arrow there. Now you can see this is all very detailed, making sure these curly arrows are right, the induced dipole is right, where that curly arrow goes there, and the positive charge on the intermediate there. You know, all of these small points are all adding up to quite a mark-rich question, 4 marks for getting all of those detailed aspects of the mechanism done, and that's going to mark you out, isn't it, as an A-star student. Good. Now, chloroethene can be polymerized. Well, I think easy marks here, actually. This is chloroethene, isn't it? Ethene is a double bond, and it's got a chlorine atom there. And when you polymerize that, then you're going to end up with, well, that's 1 repeating unit that was chloroethene, and then you're going to have, well, they wanted 3 repeat units, didn't they? They wanted 3 repeat units. So let's draw another one. It's a bit messy because of my computer pen. Oops. It's alternating, isn't it? Hydrogen, chlorine, hydrogen, chlorine, hydrogen, chlorine. So hydrogen and chlorine. Then there's another repeat unit, hydrogen, chlorine, and that's hydrogen, hydrogen. Now, the point is that this is, isn't it? It's a polymer. It's a long chain, all right? Now, we've just drawn 3 repeat units, but actually, you know, if we were wanting to go on, we could draw a 4th repeat unit, and a 5th, and a 6th, and a 7th. So it's really important that you put this bond at the end here to show that this repeating pattern continues. It's a repeating pattern, repeating units. You've drawn 3, but it could go on and on and on and on. And so one of the things the examiner pulled students up on and deducted marks for was if you'd just done that, then you lost a mark, because it looks a bit like some kind of hexane molecule, some trichlorohexane molecule where you've forgotten some hydrogens. So that would lose your mark. To get your full marks, you've got to have 1, 2, 3 repeat units and a bond there and a bond there, showing that this is just part or a fragment or a small section of the chain that we're looking at, and the chain repeats to the left and to the right. Okay, now we're jumping, aren't we, between alkenes and alkanes, you can see we're now talking about chloroethane. Okay, now if we deconstruct this question a little bit, what's going on here is, well, if you go this way, you can see that the product over here has had chlorine and hydrogen removed or eliminated. We've eliminated a small molecule. So this is an elimination reaction. And down here, we're taking a hydroxide ion and we're knocking out the chloride ion and replacing it or substituting it with the hydroxide ion. So that is a substitution reaction, isn't it? And so, what's going on here, not explicitly, but implicitly, is testing your knowledge of the difference between elimination reactions and substitution reactions. And to get the elimination reaction to work, you need to be in a solvent that is ethanol. And to get the substitution reaction to work, you've got to be in a solvent that's water. And they've shown you that, haven't they, here, that you've got a hydrated hydroxide ion, water is the solvent. But here, ethanol is the solvent, and you're going to be using sodium hydroxide again, but it's going to be used in the solvent in an elimination reaction. Okay, so the reagent and the conditions that you need for this reaction, well, you need sodium hydroxide. Actually, you could use potassium hydroxide as well. It doesn't really matter as long as you've got hydroxide ion. You're using ethanol as solvent. That makes sure you get the elimination reaction, not the substitution reaction. You need to heat it. And when you do conditions for these things, well, you've got to mention heat, but you've also, well, normally for these kinds of questions, you've got to choose between, are you going to be heating it to distill the product, or are you going to heat it under reflux? Now, the only time you want to distill something is when you want to remove the product as soon as it's made. Usually that's because the product itself could go on to react further. Now, once you've made the alkene here, there's no chance of any further reaction, so you don't need to remove the product as soon as you've made it. There's no need to distill it. So you just need to heat this reaction until the reaction is complete. And so we're going to heat it under reflux. So you've got 2 marks here, haven't you? And actually, to get all of the 2 marks, you've got to name the reagent, which was the hydroxide ion, and the conditions were, well, there's 3 of them actually. There's ethanol as a solvent, you're heating it, and heating it under reflux. So actually, you get your 2 marks, you're getting 1 mark for the reagent, and then to get the 2nd mark, you've got to get these 3 conditions. Alcoholic solvent, ethanol as a solvent, you're heating it, and you're heating it under reflux. Now, when you do that, when you do this step here, which is the substitution reaction, you're doing a substitution of that chlorine atom for the hydroxide ion, aren't you? Yeah. And so you're going to end up with, as a displayed formula, you'd end up with, that's the displayed formula, isn't it? Okay, that's the displayed formula, but they're asking you for the skeletal formula. Now, the skeletal formula here is, let me just draw it so that we can talk about it. I've got, how do I get rid of that? Okay, computer pen is, okay, let's just, it's the skeletal formula. And the skeletal formula, just watch carefully, it's that, my pen's not working, it's that, where you've got OH. That is the skeletal formula. Now, the thing is that the examiner said, that when you're drawing your skeletal formulas, careful here, that you should be drawing them with a bond angle of 120 degrees, which I've done there. All right. Now, if I had, just trying to understand that a little bit more, if I just drew the displayed formula for a very simple alkane, what's that alkane? So that's bromine, isn't it? Yeah, 4 carbons in a chain. Now, that's our displayed formula, but if we actually saw that molecule, each of those carbons would be tetrahedral shaped. Now, it's very difficult, isn't it, to draw something that's tetrahedral, although you can do it with the wedges that come out of the plane of the paper and go behind the paper. You could draw wedges. But with the skeletal formula, you're looking, if you like, at that tetrahedral shape, but kind of squashed flat. So each of these is a tetrahedral shape. You've got a carbon joined to another carbon, and that might be joined to a hydrogen atom, another hydrogen atom up there, and the other carbon atom going behind the plane of the paper. So you've got this carbon kind of shape here. Can you see what I mean? And so the examiner is saying that when you draw that as a skeletal formula, you've got to represent that shape as you go along this carbon chain as this sort of bent shape. And they're saying draw that with 120 degrees. So if we were to draw the skeletal formula of butane, we would go carbon 1, carbon 2, carbon 3, carbon 4. You see? So this kind of zigzag shape, this bent shape, having 180 degrees, represents these tetrahedral angles as you go along a carbon chain. And so really to get full marks for the skeletal formula, you've got to show carbon 1, carbon 2, and then this bent angle, this 120 degrees going to the oxygen. And then you don't show any more bonding, you're just showing OH as the functional group. So that's the correct way of drawing a skeletal formula for this substitution reaction. Now, we've been working quite hard on these displayed formulae here, haven't we? And we've now got to do a displayed formula for the product over here. Now, when you have sodium cyanide, then again, it's a substitution reaction. We're substituting a chlorine atom for the cyanide, which is a nucleophile, isn't it? It's negatively charged. And so this cyanide is cyanide ion is a nucleophile, and it's going to substitute for the chlorine that's there. It's a nucleophilic substitution. And we've got to draw the displayed formula. Well, the displayed formula is explicit. It shows absolutely everything that's there. So we've got that. And then the chloride ion was substituted, wasn't it? And you're making, when you know, the use of this cyanide ion in organic synthesis is to extend the length of the carbon chain by 1. So here we're extending the length of the carbon chain by 1. There it is. And because we had the cyanide ion as our nucleophile in the substitution, then the remains of the cyanide ion is a triple bond joined to the nitrogen, because this cyanide ion, if you remember, is that, isn't it? Overall negative, yeah? So triple bonded nitrogen through to a carbon, and the carbon has a lone pair of electrons on it. Now, you know, if that there wasn't that group, if you just had on the end here, just for the sake of argument, a carbon atom and an OH group, you'd have no problems in naming that, would you? You go 1, 2, 3, the stem is prop, and the functional group is an alcohol, so the suffix is an ol, and we don't have to do any prefix here because it's at the 1 position, and there's only one possible 1 position. So if you were trying to figure out the name of that, and it was an alcohol, you'd go from the stem, the 3 carbons in a row, you'd say propanol, wouldn't you? But actually, because we haven't put on there propanol, have we? We've put on there this group here. Yeah? But the stem is still 3, isn't it? 1, 2, 3. So it's going to be prop. Now what's the suffix? And what's this functional group over here? Triple bonded nitrogen. Well, that is a nitrile group. All right? And it can only be in one particular position. 1 is there. Or if it went over there, that's 1 position as well. So we don't need a prefix in this particular case. So we've got the stem, prop, and the suffix nitrile. So we're going to have the name there is going to be propan. And we could say propan nitrile. That would give us a double N, wouldn't it? So we can't do that. So we have to say propane nitrile. Okay, so we can have 2 N's together. Propane nitrile is the name. So we had to get our 2 marks here. We had our displayed formula and the name. There's the displayed formula and the name. Very good. Okay, so that's the end of our masterclass this evening. We've been through the structured answer paper and particularly picked out the areas that the examiner said were the areas that distinguish an A-star student from a less well-scoring student. And I hope that's helped you in your ambition to become A-star chemistry students too. Great, so that's the end of the masterclass this evening. If you want to catch up with the Z coaches who can talk about this past paper with you, the Z coaches are on the Slack channel for the masterclasses. So just jump on the Slack channel, and if you've got questions about the paper that we've been through today, then just raise those with the Z coaches on the Slack channel, and they'll be delighted to help you with your studies in chemistry. So thanks for watching, and I wish you every success in your work as a chemistry student.